Okay, I think we're live. Hello, everyone, and welcome to this webinar looking at the topic of CO2 enhanced oil recovery to carbon capture and storage. I am Daryl, the Climate and Energy Senior Manager at IPECA. IPECA is the Global Oil and Gas Association for advancing environmental and social performance across the energy transition. We've been championing good practice for over 50 years. And I'm pleased to welcome you all here today and would firstly like to share a special thanks to our webinar series partners, SP CCUS Technical Section, SP Gaia, OGCI, and IOGP. So as part of this webinar series, we also held a webinar on social acceptance in August. We're planning more webinars in this series, so please stay tuned and refer to IPECA's homepage for more information about future events. Today's webinar will be moderated by Shannon Gray, who's IPECA's CCS Task Force Co-Chair. And before I pass over to him for some opening words, I would like to cover some housekeeping. So in terms of housekeeping, there will be a dedicated Q&A session at the end of the webinar. But feel free to ask questions throughout, so you can do that through the Q&A function you should be able to see on your Teams page. Participants are unable to unmute or turn their cameras on unless the host enables permission. However, we still encourage you to post questions into the Q&A function. Finally, the webinar will be recorded and the recording will be shared to registrants after the webinar has concluded. So that's all from me now, and I will pass over to Shannon for some opening words. So thank you.
Thank you very much, Joe. Can you hear me okay? Perfect. Always like to check in. So welcome, everyone. This is our second CCS webinar of the year. Sarah mentioned my name is Shannon Gray. I have the honor to be IPECA CCS Task Force Co-Chair. Today we have a subject that some could say is controversial in the realm of CCS and emissions abatement. But we're hoping to answer a lot of questions today about the technology for CO2-enhanced recovery. We're hoping to get into some of the background on how the technology came about. William's going to take us through, I think, some of the fundamentals and some of the history of that out of the United States. And then have Rafael Vieira from Petrobras, who's going to take us through some of his experience exploring CO2-enhanced recovery in offshore Brazil. And then we're going to bring to Professor Sean McCoy from the University of Calgary. He's going to look at some of the life cycle impacts on some of the fuels and products that could come from the work in CO2-enhanced recovery. We're going to have about an hour for the webinar today. Each speaker is going to have about 12 minutes. I'm going to have the Q&A at the end. As Zero mentioned, please do, if you have questions, try and put them in the chat. We're going to have a few pre-populated questions, but if you do have questions, we're going to try and prioritize those from the audience today. And I feel like webinars are always more interesting when we get interaction from the audience. So we're going to try and encourage that as much as we can. And with that, we'll kick it off to our first speaker and one of my close personal friends, Mr. William Barrett. William's had a long career at Oxy. I couldn't think of a better person to give us an overview of CO2-enhanced recovery. And with that, I'll let William introduce himself and give you some insight into his depth of knowledge in this topic, and we'll take it away. See you, William.
Thank you very much, Shannon, for that introduction, and thank you, Daryl, and all for the invitation to be here today. Yeah, enhanced oil recovery to me is near and dear to my heart. It's something that I've done for a large part of my career, but it's strange, you know, something that's so normal and understandable to us in the business is very strange, and to people who have never heard of it or don't know the details of how it works, or that it's not something brand new. It's something that we've actually been doing for more than 50 years. So let me share get my screen going up here. I do have some slides that I'll work through. Bear with me for just a moment. And so it says it's loading the.
We can see your screen, William, so all good.
Okay, very good. So basically, this is kind of EOR 101. I know there's a lot of people from SPE here that you probably know this very well. There's others on here that know what EOR stands for. So basically, it's enhanced oil recovery. To start off with, this is from the attorneys. It's just a caution that there can be forward-looking statements in the presentation, and take those at face value, right? What we'll do is I'll go through just a quick introduction of myself, and then 1.5 is the company that I work for. I'm the vice president of product development, and I'll tell you a little bit about the company, and then we'll go into the basics of CO₂-EOR, kind of a storage overview of how the CO₂ actually gets stored, and then the whole process of enhanced oil recovery on the field level basis, and then a little bit about history of the CO₂-EOR in the United States, where it basically was invented, I would say, and then a case study on one of our fields that Oxy operates. So I'm, as I mentioned, let's see, my degree is in petroleum engineering, and that was from Texas A&M University back in 1988, so I'm dating myself a little bit. I also have a master's of business administration with concentration in international business from University of St. Thomas. I'm a registered professional engineer and also serve on the advisory board of the University of Houston's petroleum engineering department. A little bit about 1.5. So it is a wholly owned subsidiary of Oxy, and it's basically dedicated to removing CO₂ from the atmosphere and then either storing it or utilizing it. And so this slide, it's a little bit small on my side. I'll try to make it bigger, but not working. But basically, the CO₂ that we can get is either direct air capture or point source capture. And from those, the CO₂ is sequestered in geologic sequestration. And so we can also go with that CO₂ from the air to an air to fuels by combining that with hydrogen from electrolysis to form a sustainable fuel, a synthetic fuel. So the result of this are the products so that we can get the CO₂ feedstock that will go straight into, if we geologically sequester that in enhanced oil recovery, we can get a lower carbon or a net zero barrel of oil. We can also come straight from geologic sequestration or direct air capture into the carbon removal credits. So that will just be just the paper. So the environmental attribute can either follow the oil in CO₂-EOR, or it can go by itself, and just the oil would be normal oil, and you would sell the credit as it was generated from the CO₂ sequestered. So basically, as 1.5, we offer optionality to the customers. We can give them a CDR, carbon dioxide removal certificate. We can offer them low carbon fuels. We can offer them the raw CO₂ for feedstock for others that are making fuels or other products. And we can give them decarbonized fossil fuels. A little bit about carbon dioxide enhanced oil recovery. This is the basics. And how does it work? It's basically a miscible solvent. In the oil field, in the recovery process, there's primary production, which is when an oil and gas field just produces from the energy that's already in the reservoir, right? And then we also have what we call improved oil recovery. And improved oil recovery is like pressure maintenance. You will put water or some other something else in the reservoir to keep the pressure up, or to push oil from the injection wells to the producing wells. So that's an improved oil recovery. Enhanced recovery means that you're actually putting something into the reservoir that's going to change the physical characteristics of the crude. Now, it can either be steam, which will make the oil lighter and easier to flow, or it can be a miscible solvent. It can be a soap, such as alkaline or surfactant polymer. In this case, it's carbon dioxide under the right conditions, temperature and pressure, and composition is miscible with the oil. So it's a miscible solvent. And then how it works is, and I will say you can do immiscible enhanced oil recovery, and it has been done, but I don't think there's a single economic case of it. So they're all technical successes and economic failures. It's only when you get to the miscible stage that you get enough oil recovery that they become economical. So CO2 is injected into what can be depleted oil and gas reservoirs. It doesn't have to necessarily be depleted, but that's the way it's usually done. And it forms a homogeneous mixture. Interfacial tension relaxes between the oil and the water. It basically, if you see these three panes here, there's some residual oil in the formation in one, and number two, the CO2 is injected. It becomes miscible with the oil. It swells the oil. It allows it the viscosity to be lower, and it actually flows. So now the oil that was trapped, it becomes mobile. And that's the slide here. So these are the four trapping mechanisms when you put CO2 into a geologic formation. So the one that you'll always need to have there is a stratigraphic trap. And so CO2, even we inject this in a fluid, not a gaseous state, it needs to have, it's buoyant, so it wants to rise, similar to the oil and gas. And so the oil and gas has been trapped millions of years. It's usually because, or it's always because there is a seal there. And in this case, is the cap rock that's impermeable. The CO2, the oil, the water, nothing flows through it. It's basically like a granite. There's residual trapping as another mechanism. So the CO2, because of the wettability, and it's a new phase that's introduced into the rock, it's not been there before. And I will say, it's not injected into a cavern, right? It's injected into tiny pore spaces in a sandstone rock or a limestone rock that if you look at it, you would say there's nothing there, but it's actually like a microscopic sponge. And that's what we're trying to get the oil out of. So you have the residual trapping there. You have solubility trapping because there's brine naturally in these formations. And so some of the CO2 will dissolve into the brine that's there. And the last trapping mechanism is mineralization. So over time, the CO2 actually becomes part of the rock. It becomes a carbonate. And so that all of these are permanent and they all act in no matter what situation that you put the CO2 into a geologic formation. Those four are always there. The process overview, and I am looking to make sure I keep an eye on my time here because I could talk about this all day long. But anyway, the CO2 it's a closed loop system, right? We take this biogenic atmospheric or anthropogenic CO2 and put it into the reservoir where it goes down an injection well, and this is the rock formation where it then travels through the formation, acts on the oil that's there, the trapped oil. It releases the trapped oil. In turn, the CO2 gets trapped in its place, and then we get the production. So we produce this fluid. Now, generally, in dolomite carbonate formations, we will see that on the first trip through the reservoir, 60% of that CO2 will become produced again with the oil. And so 40% remains sequestered the very first trip through the reservoir. We then recycle that. So we separate the oil, gas, and the water. The oil goes to sales. The water goes back into the reservoir. The gas then is separated because now we have the natural gas and the CO2 combined together. So we separate those out. The natural gas goes to sales, and the CO2 gets recycled as 60%. Now, the next trip through the reservoir, another 40% of that is sequestered. So we make up, each day we have to make up 40% of what we put in there. So as you can see, after a few days, a couple of trips through the reservoir, you've got 100% sequestration. Now, the history of the CO₂-EOR in the United States, as I mentioned, this is not a new technology. The first patent for CO₂-EOR was granted in 1952, and the Texas Rail Commission, if you look at that, between 1958 and 1962 were the very first enhanced oil recovery projects in the United States and Oklahoma. The first commercial EOR project, now those were a lot of test cases, right? They were trying to make the technology viable. And so since then, it's been very well perfected. So the first commercial project was in West Texas in Scurry County, and it's called the field is the Scurry County Canyon Reef Operators Committee, or SACROC. And you can find a lot of information on this field in the literature. The very first economic CO₂-EOR project. Now, after the oil embargo of 1973, there was more emphasis on domestic oil production, and so enhanced oil recovery then became more prominent. And so now, as of 2023, a couple of years back, there were 139 CO₂-EOR projects in the United States, producing 241,000 barrels of oil a day, injecting 2 BCF of CO₂ each day. And now, I will say that historically, most of that CO₂ had come from natural sources, natural mines of CO₂ that were basically, if you look at this map, the blue zones, they were in Colorado and New Mexico, where there was volcanic activity in the past. And I will say that in the West Bravo Dome here, the CO₂ that's produced from those wells is food grade quality. It's 99 point something percent. So Coca-Cola is buys some of that CO₂, but most of it is piped down here into the Permian Basin. And so there's 1.3 BCF today that comes from natural CO₂ sources, and then the industrial CO₂, which is what we're interested in now, 0.7 BCF a day. And this just shows you what different basins, the Gulf Coast, the Rocky Mountains. Most of this is in the Permian Basin. Then you have some mid-continent, and then some of the Rockies, more recently, Rockies and Gulf Coast. Now, last thing I'll do here is talk about a little case study. And this is Oxy's operated Wasson Denver unit. Now, it's the Wasson field, and it's made up of several units. So the field is roughly includes all of these units. And so the Denver unit is the one that I'll talk about. It was discovered in 1936 in water flooding, which is an improved oil recovery mechanism where we pump additional waters into the field to repressurize it. That was started in 1960. And the CO₂-EOR injection, enhanced oil recovery, started in 1983, and it's still going on today in this field. So the estimated amount of CO₂ that has been sequestered to date since 1983 is 775 million metric tons. We, back in 2015, were able to get the very first EPA, the U.S. Environmental Protection Agency's MRV plan, the Monitoring and Reporting and Verification Plan, approved. So that was the very first one in the United States, and it was for the Denver unit. The second one was also for one of our units in Hobbs, New Mexico. So we report annually under the greenhouse gas reporting, subpart RR. And so you can look at those reports. They're available online. You can see that that what we inject, it stays in the reservoir. The amount that is sequestered is over 99%. It's and I think I'll touch on that on the next slide. So the geology is, as we talked about before, you could think of it as an upside down bowl, right? So all the buoyant fluids are under the bowl, and the bowl itself, in this case, it's over hundreds of feet thick, is the impermeable cap rock. So this is just kind of shows you the Denver unit's MRV performance. We started with one MRV for the Denver unit and expanded it to some of the other fields that are here. You see the Willard, the ODC unit. the Wasson ODC and the Bennett Ranch. So we expanded that MRV to include all of those. And the maximum storage space is 1,325 million metric tons in these fields. So you can see that it's a sizable amount of CO2 sequestration potential there. Seeing that I'm a little short of time, this is the cumulative CO2 storage to date, and then going forward, you can see the projection as we continue the CO₂-EOR project into the future. And with that, I will go ahead and turn this back over to you, Shannon, and the next presenter.
Excellent. We thank you for the overview. Yeah, it seems like you guys have more than enough material, and I do believe you would say you could talk about this all day. I'm sure you'll have some questions. We have a few going in the chat there, but we'll have our next speaker coming up. Next is going to be Rafael Augusto Vieira, who's a senior technical advisor from Petrobras. Rafael's going to share with us some of his experience offshore as we move from an experience in North America, kind of American perspective, down to South America, and the Brazilian perspective. Rafael,
Yes, thank you, Shannon. I'll share my screen. Tell me if you're seeing.
I can see it.
Yeah.
Full screen looks great.
Okay, thank you, Shannon. Thank you, IPICA, for the invitation to this talk today. It's good to talk after William because he has introduced many important aspects for my presentation. I will start my presentation with some fundamentals on EOR and CO₂-EOR very briefly. Then I will jump into the application scenario for CO₂-EOR that we have here in Brazil. There is the pre-salt basin, right? And about this, I will make some comments on the risk mitigation strategy that we adopted. Then I will talk about some big numbers, main numbers about this application, and the way forward that we see for CO₂-EOR here. And I will end up with final remarks, right? So probably everyone must have heard about it. We cannot extract all the oil that we have on the ground. In fact, the average recovery factor, worldwide speaking, is something in between 30-35% of the original oil in place that we have, which means that 2/3 of all the oil will remain there as non-recoverable resources, right? We have many reasons for that, reasons related to the engineering design of the exploitation plan. For example, the number of wells that we can drill economically, the well spacing, well type, well location. We have another set of reasons related to the way we operate the fields, right? For example, how much water can we inject to push the oil towards the producers, as well how much water can we produce and treat and overboard, right? And we have some causes related to nature. For example, rock heterogeneity. If the reservoir rock is more heterogeneous, it's harder to produce oil, right? If we have big viscosity differences between the oil itself and the fluids that we use to push this oil towards the producers, for example, water or gas, it's also harder to extract the oil. Density differences also have an impact. Immiscibility between phases is another natural cause, very important for us, because it is one of the main causes of oil retention in rock pores, right? And keep this one in mind because it's very important for CO₂-EOR, as William just presented. And the last one is rock surface affinity by different fluids, what we technically call wettability. So if, for example, the rock surface has a greater affinity for oil, it's oil wetted, it's harder to extract the oil. We have some technologies to try to overcome these recovery limitations. We have the enhanced oil recovery technologies. There are special methods that we use to modify the physical chemistry of fluids and rocks to increase recovery at field scale, right? We are talking about field-wide methods here. And we have the IOR, the improved oil recovery. That is a broader definition that encompasses not only EOR technologies, but everything else that we can do for recovery increase. For example, simply drilling more wells, something that we call infill drilling, is considered IOR. A special reservoir characterization, for example, using a special seismic or tracer campaigns, it's also considered IOR. Implementing EOR in a field is not something easy, right? Because these technologies, they are more complex, they are more uncertain, we have additional costs, they have longer payback times, longer qualification times. They compete with other technologies that don't offer the same benefit, but they are easier to implement, so they are the low-hanging fruits. And this bunch of technologies, they are more sensitive to risk and oil price. It's even more challenging if you want to go offshore, especially ultra-deep offshore, because there we have larger reservoirs. So for example, if we are dealing with chemical EOR, we need to bring there a lot of products, a lot of chemicals, and it's not easy. They are offshore fields. We have less wells, we have irregular patterns, longer response times. It's harder to adapt the platforms to receive those products, those EOR fluids that we inject, as well as the equipment that we need to do that. So we have limitations, retrofitting limitations on the platforms. And we are less tolerant to impacts on topside processes. For example, if I inject something that when we produce, it's going to harm our oil-water separation process or even the water treatment process and overboarding, it's a problem. So it's key, if I want to implement EOR offshore, to think about it in advance. We have many EOR methods. If we look carefully, each one tries to attack one of that natural causes that I just mentioned. For example, if I put polymer in the water that I inject, trying to viscosify this water, what I'm trying to do is to approximate oil viscosity and water viscosity, right? But here today, we are interested in gas-based EOR, especially CO2 EOR, and what we are trying to do is to attack that immiscibility that I just mentioned, because as William told us, gases, especially CO2 at very high pressure, they become miscible with oil. So I eliminate those causes of oil trapping. CO2 EOR is very important. Historically, is the second most applied EOR technology, just loses to thermal EOR, which means that for us, oil companies, especially in the upstream business, the U from CCUS, the utilization means CO2 EOR. And since the 70s, the 50s, right? For a long time, we know how it works and we apply it. Reasons for using CO2 EOR that much. First, we have multiple powerful and well-known mechanisms. These mechanisms, oil swelling, viscosity reduction, extraction, miscibility, they can reduce SOR, that is residual oil saturation, that oil that becomes trapped in the rock pores, to almost zero, where gas effectively can contact this oil. It's something scalable as far as we have access to the gas, to the CO2. And historically, we have had access to these sources of CO2, especially onshore USA, as William showed us. We have their natural sources of CO2. So that's one reason for the great use of CO2, worldwide speaking. So one important message here, CO2 for us from the recovery point of view is not a problem, it's a solution. It's a valuable and magnificent fluid for EOR. We can have an impression about the power of CO2 if we perform very simple lab experiments. For example, in this one, we had a piece of rock saturated, full of oil, fully saturated with oil, and we have injected water up to ceasing the oil production. So in these first test tubes, we see that we injected water and it produced just water. right? We just circulate water here. We were not producing oil anymore. As far as start injecting CO2, the oil started to show up again by all those mechanisms that I mentioned. But life is not a bed of roses. We have issues too. And the main one is related to gas, very high mobility in the rocks, right? Gases, even at high pressures, they are very low viscous. So they tend to pass through the most permeable pores of the rock. That's what we see in this micromodel experiment performed by Harvard University. Here we see the CO2 bubbles flowing very quickly through the most permeable pores, leaving a lot of oil behind, right? So gas can extract all the oil where it contacts this oil, but it doesn't sweep very well the rock. We have ways to overcome this issue. One of the ways is to implement WAG technology. WAG means water alternating gas. What happens is when I alternate water cycles with gas cycles, this water blocks the pores, the preferential pores where gas was passing through, causing gas diversion and the production of oil from these adjacent pores. So simultaneously to oil production, to increase the oil production, we also have gas entrapment, right? So here, by performing WAG, I have a synergy between the better displacement efficiency of gas and the better sweep efficiency of water. Which means that, in other words, the same amount of gas can do a better job. Now talking a little bit the application scenario here in Brazil for CO₂-EOR. It's the pre-salt basin. It's located southeast Brazil. There we have some big and giant fields. They are carbonate rock fields that possess light oils and a huge associated gas content. We have a lot of gas dissolved in this oil. And one particularity, this gas is contaminated with CO2. Percentages of contaminations can range from a few percent units up to 45% molar of CO2 in this gas. Petrobras and its partners, since the beginning, decided not to vent the CO2 in the atmosphere. We decided to reinject this gas. By doing so, we could join environmental compliance with improved gas management and EOR. Gas, as I told you, is a very good extractor for oil, is a very good solvent for oil, let's say like this. And here we have favorable conditions for gas injection. For example, we have high pressures. We are talking about 6,000, 7,000, 8,000 psi. Low temperatures from 60 to 90 Celsius. Light oils and CO2. So we have favorable conditions for miscibility. CO₂-EOR is not something new, as William told us, but it's not very usual to do that in offshore environment, especially ultra deep offshore, right? So we had risks involving this application. To mitigate those risks, we tried to implement a risk mitigation strategy based in 4 pillars: reservoir characterization, reservoir modeling and simulation, a field pilot, and the development or adoption or some WAG enabling techs. Regarding characterization, we performed a very broad fluid characterization program involving not just the standard PVT tests, but also some tests, special tests related to CO₂-EOR that are swelling tests, minimum visibility pressure tests, interfacial tension tests, and asphaltene precipitation evaluations, right? We also performed a broad multi-phase flow in porous media characterization, investigating those zones that are not usually investigated in normal water floodings. So we investigated experimentally the WAG three-phase zone, the two-phase gas oil zone, the miscible zone, right? In the field, we implemented a very broad tracing characterization program involving gas and water tracers, mainly to better characterize the reservoir, to monitor WAG cycles, and to detect miscibility at field scale, right? In terms of reservoir modeling, we started evaluating the models that we have available in commercial simulators to see if they fitted the phenomena that we wanted to represent. Then we started performing some evaluations in sector models, upscale the parameters, and finally perform the field scale WAG simulations. In terms of enabling technologies, those technologies that we need to bring that application to the field in reality, we adopted or developed CO2 separation by membranes, gas drying by molecular sieves, adopted the intelligent completion in order to inject the gas where we wanted to. We installed simultaneous gas and water manifolds in the field, which brings a lot of flexibility. We studied the corrosion and adopted corrosion-resistant materials, adopted a flow line inspection and management procedure, because here we have a problem that we call stress corrosion cracking. You probably know that CO2 in contact with water is acidic, so we have corrosion issues. Scale removal and prevention, because carbonate rocks, they are more reactive, especially when we have CO2 and water. So we need to adopt that scale removal and prevention procedures. The gas tracing and water tracing that I just mentioned, and rock fluid interaction modeling and simulation. Regarding the pilot, it was done in Tupi field here in pre-salt, mainly to test the WAG operation, the cycling, if we would have some problem, test some WAG enabling technologies, evaluate the performance in the field, confirm some lab observation, and reduce risks for expansion. The results were good in such a way that now we have expanded CO₂-EOR and WAG to 10 fields here in pre-salt, involving 70 wells, and we have so far done more than 200 fluid switches successfully. We have stored, re-injected, in fact, 70 million tons of CO2. Tupi field, as I told you, was the pioneer and is considered one of the biggest offshore CO2 EOR injection worldwide. And our average estimated benefits around 1–2% units over continuous gas or water flooding in dedicated wells, right? So in literature, we have a little bit more, like 10%, but remember we are offshore, just a few wells, just dealing with associated gas. So this amount is more modest, but for our giant fields, 1–2% is a lot of oil, a lot of money. Now the way forward that we see for the application, we intend to further improve WAG performance by optimizing the cycles and adopting additional gas mobility control technologies over WAG, expand to new pre-salt areas, and we see offshore CO₂-EOR as an enabler for future CCUS and CCS projects. Maybe in the future we can use more CO2 in these fields as this fluid tends to be more available in the future. And maybe we can boost CCUS projects with carbon credit revenues in the future. Another thing that we consider very important is one proprietary technology that is being developed. It's HISAP. It's named HISAP. It's an instrument, an equipment that will separate the CO2-rich streams on sea bottom, right? On bottom floor of the sea. In such a way that we debottleneck the platform. We can re-inject, separate and re-inject these CO2-rich streams directly from seafloor. Now the final remarks to end my presentation. CO₂-EOR was successfully implemented in pre-salt. Phased approach was important for flexibility, robustness, and risk mitigation. The cumulative re-injected CO2 reached 70 million tons by this year. The experience that we are gaining here by doing this CO₂-EOR may be an enabler for future CCUS, CCS initiatives in deeper waters. And my last message, CO₂-EOR recovers more oil, jointly stores a significant amount of CO2, as William told us, not all of the gas that we inject we back produce. Part of it, and a good part of it, remains there stored, and it helps to pay out for capture and storage costs, right? So here are some acknowledgements for Petrobras employees that deals with these projects, and to Petrobras for permission to present these slides today. Thank you.
Excellent presentation, Rafael. Thank you so much for that overview of your experience offshore with Petrobras. So we've started in North America. We've had some history with the development of technology. We've seen how it's expanded offshore in South America. We're going to go back to North America now to talk to Professor Sean McCoy, who's going to take us through some of the carbon accounting and life cycle analysis of how you actually look at the environmental impact of these systems on a broader, more holistic scale. Whenever you're ready, Sean.
Great, thanks very much, Shannon. So I'd like to say good morning for me and good afternoon or evening for those of us, for those of you joining from other places in the world. So I'm joining today from Calgary, Alberta, and that's the home of the peoples of the Treaty 7 region in Canada. Those include the Blackfoot Confederacy, the Tsuut'ina, and the Stoney Nakoda. And we're also home to the Métis Nation of Alberta, and it's very important for us to acknowledge these First Nations peoples here in Canada. So I want to take a moment to do that. So I'd like to just talk about CO2-enhanced oil recovery. We've heard a lot about the technical side of it, but I want to talk about it from the emissions reduction and the sort of CCS standpoint. That was sort of in the title. So thinking about how does this relate to carbon capture and storage? And so I want to start from, I think, a point which many people here would sort of understand intuitively, which is to think about carbon capture and storage. And so without EOR, so thinking about storage of carbon dioxide in a saline aquifer. And the key point is that when we want to do CCS, we want to reduce emissions to the atmosphere. And the thing to make sure you kind of disconnect your head from is that this isn't about storing CO2 in the ground necessarily, right? It's about reducing emissions to the atmosphere. And those things can be correlated, but they're not directly related. So let's take a look at this example that I'm showing you here, where I basically have a gas-fired power plant, okay, a natural gas combined cycle. And in that case, the facility it's burning carbon dioxide today, and I'm using a combined cycle power plant. It could be anything else. It could be a steel mill, a cement plant, you name it. It burns natural gas, and so we see all these emissions from combustion of that natural gas. Makes perfect sense. And then we have some upstream emissions from natural gas supply, right? We all know that that happens as part of the production cycle, and some emissions from constructing the plant. If we add that all up, we get sort of this 450 sort of rough number, kilograms CO2 per kilowatt hour of electricity, okay? So we're talking about those are the emissions from that plant to the atmosphere. If we add carbon capture and storage, of course, we're capturing that CO2. Great. And of course, we are storing it. And we have some increased emissions from the upstream cycle because of the increased energy efficiency or the increased energy use, decreased efficiency of the power plant, and a bit more construction emissions. But the point here is that we have this big emissions reduction, right? And that's sort of like 65%, right? And that's the benefit of CCS. And that's what we want to see happen through CO₂-EOR. But of course, we have to think about this from the life cycle. And so if we look at the life cycle of the example I just gave, and again, this is for electricity generation, and that's a simple one, because when we think about electricity, we know that we produce a product that has no carbon associated with it in its use, right? We don't burn it or anything. It's just, it's pure energy, right? And we have to look at the production chain, as I mentioned, from production through processing, transport, and eventually that generation of electricity. And when we think about that, we're talking about what's known as the cradle to grave life cycle, right? And inside that is the CCS component, or the geologic storage component. So if we extend that to EOR, and we think about what William was saying, the origins of EOR in the United States, where CO2, and even today, right, a large portion of the CO2 used to enhance oil recovery is coming from natural accumulations, right? That goes through transport, that large pipeline network you saw on the map, through use and enhanced oil recovery, which we've heard quite a bit about in the technical operations of it. And then we produce that oil, gas, and natural gas liquids. That's the benefit of this whole process and why we would be doing it. We transport that to the refinery. Those refined products and petrochemicals are eventually distributed and used, right? And supporting the life we have all around us today, transportation, plastics, various petrochemicals. And so we could think about that from several different perspectives. We could think about this from a gate-to-gate perspective and look at just the emissions from that one component of the system. We think about well to pump, and so many of you might have heard that term before when we think about carbon intensity of fuels. And then we think about, again, the cradle to grave on this, and we're putting everything in there, including the end use of the products. Okay, and in the fuels area, that's often referred to as the well to wheel carbon intensity. So if we want to put EOR together with some other production route to reduce emissions, we have to look at these two parts of the life cycle and connect them. So we have our power generation component. That makes sense. We've looked at that. We have to transport that CO2 and use it in capture, transport, and use it in EOR. And so now we have an EOR life cycle. And where this gets interesting is we now have two different sets of products that result, right? One is whatever we set out to make in the initial case, whether it's cement, steel, fertilizers, electricity, as in this example, and those products. And so now we want to look at the cradle to grave impact of everything happening here. And why do we care about that? Because that's what the climate cares about, and that's what we're trying to address here. So let's try to look at the question of, could CO2-EOR then reduce emissions across that cradle to grave life cycle? So I'm going to work through a little bit of a thought experiment here, okay? And so I'm going to talk about something first called a marginal system. And in this marginal system, okay, I am producing oil, as I would. Let me get my slide to move forward here. There we go. Okay, I'm producing oil as I would today, somewhere in the world. We'll say that's Saudi Arabia, because certainly maybe Saudi Arabia or maybe a US tight oil producer or something like that might be on the margin of the market today. And so I'm producing oil, I combust that oil. I also have a power plant. It emits carbon dioxide, just as it did in the first example, and I have all the emissions associated with the rest of that in this bar here. And so those emissions end up being close to 1,000 kilograms equivalent, and that gives me 1 barrel of oil and a little bit of electricity, right? And the ratio of the oil to electricity depends on how much CO2 is used per barrel, basically, in an EOR project. If I then add carbon capture and storage, I'm going to reduce emissions, right? Because I capture carbon dioxide that eventually goes to an EOR project. And because enhanced oil recovery is quite energy intensive, as has been alluded, we have lots of recycling and compression that happens. We have some increased emissions because of that switch to EOR. But the net is that I have fewer emissions, right, than I would if I was just producing oil and burning gas for power. And so that reduction, what we see here, and this is in this example, something like 200, 300 kilograms of CO2 equivalent, right? That reduction could be attributed to the barrel, right? And in which case you'd say that the EOR can reduce emissions by 300, give or take, kilograms per barrel. Or, right, you could attribute it to the power plant, right? And say that the power plant was, through this activity, is reducing emissions by something a little less than 300 or 284, because we have to divide by 1.07, okay? So a little bit less. So either way, this whole system gives us a reduction, and we can play around with how we're going to attribute it to one activity or the other, right? But that's a good thing. Now, the one challenge when we think about this is that this is based on some basic assumptions. And honestly, those are assumptions that not everyone's going to agree with. And so you have to assume that the emitter in the power plant or whatever it is would continue to emit carbon dioxide to the atmosphere if you didn't do this CO2-EOR based storage system. You'd have to also assume that the barrels of oil that you produce through the market substitute for someone else's production in the world, right? And those marginal barrels in that marginal system I described will not be produced. And of course, if you want to do this from a quantitative perspective, you have to actually know who the marginal oil producer is in the marketplace and what their emissions are. So if we think about that for a given specific project, these assumptions are almost impossible to verify, and they're very difficult to work out, right? And so these results are, I think, more useful from a policy perspective, because they certainly do suggest that relative to what we do today, CO2-EOR can bring about an emissions reduction. And this isn't completely made up or artificial. This is actually sort of a way that we think through doing life cycle assessment, a formalized way called substitution. But if you don't think these assumptions hold, or you want to compare barrels, and I say this because often in oil and gas, we want to compare the greenhouse gas intensity of different barrels from different fields, different producers, different countries, regions. There's a different approach called allocation, okay? And I'm going to do an example here where we can allocate emissions, and we'll start off with those emissions that I showed from the system. Oh, okay, emissions from the system, just like in the previous graph on the far right-hand side, I talked about the system having emissions of something like 600, 700 kilograms of CO2 equivalent, and that resulted in a reduction. In this case, I'm just talking about I have absolute emissions, right? And those are attributable to both oil production and electricity production. And if I assume that there's a certain value of carbon dioxide versus a value of electricity, I can then split the emissions across the two different products, and I get electricity with a very low carbon intensity and oil with something which is close to the global average in this particular example of crude. So the global average is about 512 kilograms CO2 equivalent per barrel, and these results give you 528. Okay, and so these, and I'm using numbers here that are from the median values from a study that I was involved in, where we looked at, excuse me, jumped too far. We looked at all of the published studies, and so these are largely academic with maybe one exception. And we looked at what they had said about the emissions from CO₂-EOR projects. And if we take that latter approach, allocation, which you could use to compare barrels, we find emissions factors that runs from a low number of 359 kilograms per barrel, so quite a bit lower than the US average, or than the global average, to 693, so quite a bit higher than the global average. And if we think about a substitution approach, right, where I'm actually explicitly trying to look at how barrels of a marginal system might be displaced, we can find emissions reductions that range from 35 to 739 kilograms equivalent of CO2 per barrel. And that's shown on, of course, these two panels with the allocation approach and the substitution approach. And I just note that these negative numbers here denote a reduction, and they are not to be thought of as negative emissions. So could projects do better than this? Absolutely. We've heard and know that we have a lot of compression energy, and if we do natural gas liquid separation, energy that goes there for these projects. So if that can be done more efficiently, great, that is of a benefit to emissions, and we can also seek out decarbonized electricity for these processes. We know that across oil and gas systems, venting, flaring, and fugitives aren't always well tracked. That's, of course, improving, but EOR project should really measure and report venting, flaring, and fugitives much more than they do. And finally, we could actually talk about engineering the projects differently and think about how you could increase net utilization. And from that emissions reduction perspective, you're using more CO2, you're storing more CO2, and effectively you can you get more CO2 stored for every unit of product that you would produce in the system, which could be beneficial. So I guess I'll wrap up just a few take-home messages that I think indeed CO₂-EOR does have that potential to reduce emissions, but there is always a baseline question and that people can have disagreements over. But we can always do an allocational approach to compare barrels, and it does show that you can generate some low emissions products out of the system. And there are practical ways to reduce emissions from these projects, and that what would be great is to have more data so that we don't just have to rely on sort of academic studies. So I'll stop there. Thank you.
Thank you very much for that overview, Sean. If I could get all of the presenters to come back on camera, we have just about 6 minutes left to wrap up Q&A. We have a lot of questions in the chat. If people have time, we may go a minute over, but probably not much more. I know most of you are busy. We can also potentially answer some of the questions in the chat through our IPICA resources. So if you guys want those answered, let us know. We'll see if we can reach out through email. But I'm going to dive in and use the time that we have with the speakers. I've been kind of going through the questions. There's been a few themes that come up. One theme that I wanted to go through, or a question I wanted to address, was some questions in the chat around how much of the CO2 used in an EOR field is actually stored. I'd like to throw that question out to William and to Raphael, and also follow up with how do we know this is stored, and then how do we measure this? And I saw a few questions in the chat around how much is stored and retained, and then how is that measured and reported. William, if I could maybe get you first, and then Raphael after that.
Sure, I will do that. And the amount of CO2 that's sequestered that's put in enhanced oil recovery is the literature says it's 99%, over 99%. In our over 50 years of experience, I can tell you that for us, it's less than 0.1%. The confusion comes about as far as the recycled CO2 that comes out. So as I mentioned, about each cycle through the reservoir, 40% gets sequestered. The other 60% gets re-injected, where it then acts on a different rock, and another 40% of it gets sequestered. And so if you look at the Denver unit, the example that I had given to you, it's been injecting since 1983. 99 point whatever percent of the CO2 is sequestered permanently. If you were to stop that today, the amount of CO2 that was injected yesterday, you could say 60% of that little amount would not be sequestered. But what we do on these EOR projects is we don't just stop it that way. We stop the CO2 injection and continue with the water injecting in a cycle, so that the produced CO2 does get re-injected and then stored in the reservoir. So you can say with confidence that over 99%. Now, how do we know that gets sequestered? That's the monitoring, the reporting, and the verification that regulatory bodies such as the EPA approve these plans. So what we do is we have monitoring wells. We have various different things, but we will say there's monitoring wells above the sequestration zone to make sure that nothing has leaked through the cap rock. We have on the edges of the reservoir to make sure nothing is migrated laterally. We have on the surface soil gas monitoring wells so that we can see if something was not detected there, did it make it into the subsoil. We can measure the water, the potable water zones. We have simulation, reservoir simulation, that is mass balance. So there are many, many different layers of the monitoring and reporting and verification that assure us that the CO2 remains sequestered and stored. And I think now, Raphael, I'll probably handle off to you to get your take on that.
Thank you.
Yeah, thank you, William. We are just calculating this number right now, so I don't have exact numbers to give you, but I can tell you about the way we try to do it. We try to do it by reservoir simulation, right? Very well parameterize it, so we get the parameters of all those mechanisms of retention that we have. For example, in the lab, a single mechanism that is residual trapping of gas can reach about 30% of gas trapped in the rock, just a single mechanism. So we try to input that in our simulation, numerical simulators, and get an impression about these numbers. And later on, we can do it by volume balance. We know how much we inject, we know how much we produce, and we can do a volume balance, a mass balance in the reservoir. So that's the way we try to do it. But I don't have the exact numbers to give you.
Thank you for the answer, Raphael. Moving on, I think the last question, Sean, I'll give you kind of an interesting one. I've had some questions in the chat around incentives for trying to capture CO2 from point source as opposed to natural. One of the questions, a fairly broad question, was, in your opinion, what are the technologies and some of the cost incentives and policy incentives that could help anthropogenic CO2 be captured and potentially used in CO2?
Yeah. So, I mean, traditionally the biggest, and William would, and others might want to nod or shake their head at this, but I think that traditionally one of the biggest costs, right, is that supply of CO2 to these projects and the cycling of that CO2 around. So, to the extent that effectively the cost, and you think about how this works out in the economics, but the cost of that CO2 can be reduced, right? That will make enhanced oil recovery projects more attractive. And then you have, how the revenues get shared around from these projects and amongst things. But so tax incentives are things like in the United States, I think have been quite successful at getting more capture done. And in Canada, we have those incentives too. In Canada, they don't apply to EOR. So if you want to capture CO2 to put it into EOR, unfortunately, they don't go there. But those tax incentives towards capture can be, I think, quite useful. And I know that historically, sort of, there's been a lot of focus on royalty sort of relief programs and things like that in countries other than the United States. Like Canada has, we had a lot of EOR projects in Alberta that were piloted under these soil royalty relief frameworks, and so those I think can be attractive too. But in general, right, if you do have, of course, sort of a cap or a pressure tax on emissions, right? That will also certainly drive capture of carbon dioxide, and I think CO₂-EOR is well placed to catch that CO2, if you will.
William, Raphael, anything to add?
Now that covers it pretty well. I will just say that the amount of CO₂-EOR that's done today is done in close proximity to where there is a CO2 source. If we do have incentives for point source capturing and more direct air capturing, then that can be done where the oil fields are located. So those are, now we can bring the CO2 to more oil and gas fields. And basically, it's what we're producing is a decarbonized crude.
Right. Daryl, I'm gonna look to you. I know we're at 9:02. I'm gonna assume that we need to wrap up for the audience. Just wanted to say thank you so much to our speakers, William, Raphael, Sean. Thank you so much for the time, for the expertise. Hopefully, we can reach out to you to answer any questions that made in the chat. We did get some excellent questions. I want to try and facilitate those as much as we can. Our role here at APICA is mostly to reach out, to convene, and to educate. Daryl, anything to add?
No, and thank you to the speakers, thank you to the audience, and thank you to the co-sponsors as well. And we'll see you guys soon. So thank you very much, and we'll finish the webinar there. Cheers. Have a good rest of the day, everyone. Thank you.
Thank you so much.
Thank you.
Thank you. Bye-bye.